Welcome to the first episode of Thinking Out Loud series, which is an experimental series that I am trying out on my channel, where I will attend any Div 2 or Div 3 or Div 4 contest and try to solve them live in this video without looking at the solution. So I will try to upload these videos immediately after the contest ends. I do not know if I will be able to solve any problem honestly at all, since today's is a div 1 plus div 2 round, but we'll see how it goes. I might try some approaches, I might try to brainstorm some ideas, some might work, some might not work, because all these scripted videos that you see on my channel, even though I give you a very clear train of thoughts that first you think this and then you think this and then you think this and you finally arrive at the solution, the reality is far different from it. In reality, I actually think about a lot of things at once, and then I only show the most intuitive idea in the video. Because if I were to add a lot of approaches that does not work, then people would get bored. So they are just looking for the solution that works, right? Nobody wants to look at an idea that did not work. But in this series, like in Thinking Out Loud series, I might lead you into a wrong direction for a certain problem using some idea that might not even work. And that's kind of expected. And feel free to skip the problem and maybe jump to the next problem. I will also link the chapters so that you can directly start at a particular problem instead of having to watch the entire video. And I will also write some indication somewhere whether I was able to finally solve the problem or not after all of these brainstorming, because there is no point of you watching this video if I tried a bunch of things and then none of them worked. At least one of them has to work, and if we can achieve then we are good. So the round has already started, and let me look at the first problem. So first what I'll do is, let me copy the problem statement to our whiteboard so that we can discuss about this problem and then maybe try out some test cases on the whiteboard itself. So let me create a new page over here and let me clip this part. Okay, first line is fine. Maybe second line might be important. So input, output. Okay, let's also clip that. Add it to the current page. Now let's look at this problem. What is it even trying to say? So it says that this contest has n problems. Okay, each with a full score of 100. The ith problem has AI subtasks, and each subtask has a score of 100 upon AI. Okay, it is guaranteed that AI is a divisor of 100. Of course, it has to be for the score to be a positive integer. Now, several contestants will participate in this contest. Suppose a contestant solves xi subtask of the ith problem. And of course, if there are AI subtasks of the ith problem, then they can only solve up till a maximum of AI subtasks. So this constraint wasn't really needed to be specified. It is kind of implicit. His score on the ith problem will be xi into the score of a single subtask, which also kind of makes sense, right? It did not have to be specified, because if one subtask gives you this score and you have solved xi subtask, then your total score should be equal to xi into the score of one single subtask. So the total score of the contestants in the contest is the sum of the scores on all the problems. Okay, so far so good. This also makes sense, like if there are 5 problems and for the first problem you have solved 2 subtasks, For the second problem, you have solved 3 subtasks. And for the other problems, you have solved 4, 4 and 4 subtasks. Then of course, your total score will be the score from the first task, first problem, second problem, third problem, fourth problem, and fifth problem, and you sum them up. So this also makes sense intuitively. So to prove that the contest is a truly wonderful one, okay, what does it mean? You have to check whether it is possible to achieve every integer total score, every integer total score from 0 to 100 into n. Okay, this is now getting into a bit weird territory, but let's see. Formally, you have to determine whether the following statement holds. For every integer k, where k in 0 to n, 0 to 100 into n. So what does 100 into n mean? I think this means 100 into n means you have got a perfect score on all the subtasks. So you basically, if you solve all the subtasks, so the result from the score from a single subtask is 100 into AI. And if you solve all of them, your score will be 100. And if you repeat for all n problems, the total score will be 100 into n. So that's good. But what is it saying? So this is actually the maximum score. Okay. So this means it is asking you maximum score, you know, that is 100 into n. That also did not need to be specified if you think about it. But the question is asking, is it possible to achieve all scores in this range? But how exactly? So it says for every integer k, where k is in this range, that's fine. There exists an array x of length n, okay, such that you can achieve that score. Okay, got it. So this time, so in this problem, actually, you are not really given the scores array anymore. Like you are not given the total number of problems that you have actually solved, the total number of subtasks that you have actually solved. You are only given the number of problems that you have and number of subtasks that a particular problems has, and each subtask is from 1 to 100, and of course it will also be a divisor of 100 because the score is an integer. So now it is asking you to find, is it possible to compute all the scores between 0 to 100 into n? Okay, so now that we have read the entire problem statement, let us formalize it. Let us embed it into our brain so that you don't have to go back to the problem again and again. So you have an array of length n, and let's keep in mind that n is actually very small. So n is only 10. So maybe a brute force algorithm might work for this problem. And the array elements have a1, a2 up to an, where ai divides 100. But how many divisors are there for 100? So I don't know if the number of divisors will make any difference at all, honestly. But doesn't hurt to check the number of divisors for 100. So you know that every divisors can be split into two parts. One is from the square root, one is from the left half of square root of v, and one is from the right half. So square root of 100 is 10. So this means, so one is a divisor of 100. So the other pair is 100. That is also a divisor. 2 also divides 100. Other pair is 50. 3 does not divide. 4 divides 100, the other pair is 25. Okay. 5 divides 100, the other pair is 20. Does 6 divide 100? No. 7 does not divide. Does 8 divide 100? So 100 is 25 into 4. So of course 8 cannot divide. 9 also does not divide. And 10 divides 100. The other pair is also 10. So what are the unique divisors that divide 100? They are just 1, 2, 4, 5. Then you have 10. You have 20. You have 25. You have 50. And you have 100. So this information might or might not be helpful, but just noting it down, and I will highlight it in a red box in case we need to come back to it. But this does tell us that the number of possible AIs has to be from this set only. So how many elements are there in this set? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, so there are total of 9 elements. So AI can be one of 9 values. One of 9 values. Okay. Now let's look at the constraint even before solving it. So it says that n is less than 100, but you have to find out whether the score is between 0 to 100n. So they are talking about 0 and they are also talking about 100 into n. So even before solving the problem, this might give us some hint that the maximum possible score could be 1000, right? So if we fix a particular score S and notice that there are no test cases, or are there any test cases in this problem? Okay, there are, but I think the number of test cases is small. Let's first of all ignore. So if you fix any S and if you can answer whether a particular S is achievable, and since the total number of possible S is 1000, so even if you end up doing, like, let's say S, or like even if you end up doing S square computation, then you should be good. Like for 1000, 10 to the power 6 should be acceptable. But okay, enough about these constraints. Like, we are not actually solving the entire problem, we are just trying to see what we can optimize, but optimization can only come in when we actually solve the problem. So how do we solve the problem? Now again, the idea that you are actually given all the possible score for each of the problem. So let's start fresh, and this time you have the array with you. Length of the array is just 10. And you have to compute whether you can create score is equal to X. How would you do this? So you have A1, A2, A3, A4, and so on. So you have to find some series of Xi's such that this expression, like this expression that we had seen for the score of a single function, was xi into 100 upon ai. So you do something like, first of all, you have this array. Let's not deal with, so you can see that this 100 upon ai this will be a constant, like not really a constant, but this will be fixed for a particular fixed AI. So instead of dealing with this fraction that might confuse us, why don't we just create an array, and let's say this is the like let's say we call this as the p array, which is the partial score of a problem. So this is the array that denotes the number of subtasks of a problem. So this is number of subtasks. And here you are given A1, A2, A3, and so on. And let's create another array P. And this time you say that this is the partial score for each problem. I mean, right now we are not solving the problem, but just simplifying things so that this division does not confuse us in the future. So P of I will be equal to 100 upon A of I. So once you have computed this P array, you have to find out whether you can get a sum equal to X, or let's fix it as score should be equal to S, not X, so that it doesn't confuse us. Let's fix a score as S. So this equation must be satisfied, that is S should be equal to what is the partial score of the first problem, or the what is the partial score of the ith problem, that is P of I, and what is the number of problems that you have solved for the ith problem, that is Xi. And Xi of course should be less than or equal to AI. That part you have been given, because you cannot solve more than the number of subtasks that you have. And S would simply be the summation of this. So your PIs are fixed, and you have to find out whether you can select some of these Xis. Now, how many possible values of Xis are there? So in the worst case, AI can be equal to 100, meaning there are a total of 100 subtasks with 1 credit each. So the number of possible Xis is 100. And there are 10 such entries, because n is equal to 10. There are only 10 problems. So can we try out all the possibilities? Would that even work? So one problem has 100 subtasks, worst case, but then you have to independently try out all the combinations, right? So it's not 100 into 10 different combinations. It is actually 100 to the power 10. This is the total number of combinations that you can get. So of course, brute forcing or enumerating all the Xis is not an option. So how do we solve this then? So actually we are not able to make any progress here. So let's try something new. And this time, let's see whether we can try to construct the answer using some computations from the previous round. So we know that the array is of length n, and suppose these are the length n, and maybe we can use some dynamic programming kind of idea. It might or might not work. Let me try something. So suppose you know for all of these n minus 1 elements, you know how many unique scores can be computed. Suppose you have them in a set, you store them in a set. This is a set, and this contains unique score, unique scores from n minus 1 problems. So this is like a DP idea that I'm exploring. DP might be overkill, might not even work, but let's see. And this is the new element that you want to append. Then notice that even though we said that the number of possibilities for each problem could be 100 to the power 10, but if you are just maintaining a set, the number of elements in the set, that can only be 100 into n. Basically, that cannot exceed 1000. That part we already know, because this is the maximum total score that you can get. And why is that? Because in each round you can solve all the sub problems and get a score of 100 and no more than that. So if you have processed n elements, there can be only a total of 100 into n unique scores that you can achieve entirely with the n elements. So that is good. Maybe this constraint was designed for this set based solution. I don't know. Now what happens when you append a new element? Suppose this is the nth element you want to append. Then you already have all possible combinations of the scores written down over here. Then when you append a new element, does it actually care what you do with all of these elements on the left hand side? It doesn't. It will just explore all of the possible state that this problem could live in. So suppose the value that lives in over here is a of I, and suppose the partial score at this position is p of I, and which is nothing but 100 divided by a of I. Then there are a total of AI subproblems. So if there are a total of AI subproblems, and we know that AI can only be a maximum of 100. So in the problem that you just added, you can either solve one problem or two problem or three problem, two subtask I mean, or three subtask and so on. You can solve up till AI subtasks. So why don't you solve all of these? Why don't you try out all of these possibilities? And then you compute what are the scores that you can get on this problem. So what are the possible set of scores on this problem? That is nothing but 1 into pi, 1 into p of, sorry, that will be 1 into p of I, because pi is the partial score of a single subtask. So how many different scores you can get on this problem alone? That is nothing but 1 into pi, 2 into pi, like you solve two problems and you get the partial score for each of the problem. You solve three problems, you get the partial score for three problems up till ai into pi. Okay, so how many unique elements can be here? There can be only a maximum of 100 elements. Why is that? Because ai. And now you can see that actually finding out the number of divisors did help us, even though the exact value doesn't matter, but we know that the number of divisors can be at max 100. So this list also has to be at max 100 only. And the list on the left hand side, the set that you have, that can be of length at max 1000. Therefore, you can see that on the left hand side, all the problems, all the n minus 1 problems, they can exist in one of the 1000 states, and this problem can exist in one of these 100 states. Then what about the entire set? Like, what if I ask you to answer the problem for this version? Like, you have n elements, how many unique sums can you create? So you can see that the left part is independent, right part is independent. So this means that the total number of unique ones could be as big as 1000 into 100. Okay, but this actually won't be that big, because after this round it might look like that you are creating a set of size 10 to the power 5, but this will actually get compressed to just 1000. Why? Because we know that once you do the combination of this to this, the total number of unique score can only be 1000 into n. That part we have already discussed. And why is that? Because this problem, even though it produces 1000 new entries, when you add one entry from here and one entry from here, like, they will already be in your set. So the number of elements in this set will not grow beyond 1000. So now the question arrives that, can you afford to do this 1000 of the existing set multiplied by 100? Like, uh, can you iterate over each element on the right set and then add it to each element on the left one and then plug it into a new set? Can you afford to do that if you can kind of guarantee that the new set will have unique values? So I think the time complexity here is 10 to the power 5 for a single n, and maybe we will do this operation for n rounds. Yeah. And anyway, in just the first round the number of possibilities won't jump to 1000. So I think this looks like a good solution. I think we can start the implementation. So the idea here would be to start out with a DP like approach, where you start out with an empty set. This is your unique score set. And then you process elements from left to right. You keep on processing elements, and suppose you are at this element and you want to insert a new element over here. So you have to look into your unique set, and you have to, for this element, you have to construct a different set, this one. You have to create now score, and these will contain AI different elements, and then you have to merge these sets to create next score, right? For the next round. Next round will only care about what is the unique scores for the first n elements. Next score. So idea looks correct. I don't see any obvious flaw with it, unless it might get TLE, which I doubt, because I mean T is also 100, so maybe we might have to reduce some log factor or something, but we'll see. Since it's just problem A, it should not be too difficult. But so let's jump into the coding part. And I haven't given a contest in a long time, so I might be making very silly mistakes in the coding aspect, so bear with me. Let's define a solve function, and here they are only giving you n as well as the array as an input. So okay, we'll take n and we'll take the array as an input. Now let's write the logic. I hope you are able to see my screen. Let me also actually increase the font size. Yeah. And let me also set the rulers Mm, yeah, I have to set some rulers. So rulers are already set. I don't know why it's not visible. Okay, we'll figure that out later. So, okay, you have n, and in fact, you don't even need to take in n. You can just take in a vector. Just do some fancy things like n is equal to 8 dot size. Actually, let me reduce the font size. Might be an overkill, and let me remove the left section so that yeah, actually the ruler was available on the right hand side. Now if I zoom, yeah, now it's better. So you want to maintain a set called unique scores. This is the number of unique scores that you have seen so far. And if you have zero problem, then the number of unique scores would be 0, because no problem means you do not have any score. This score is 0. So I will insert 0 over here. Now I process all the elements from left to right. So I will do int element, or let's say ai n a, or why even do all of these fancy things. I'll just do this for int I0 I less than n I plus plus. Now I have to create the p array for the partial score. So I do something like vector int p of n for integer I less than n I plus plus. I might do something like p of I is equal to, this would be simply 100 upon ai. So we know it will be divisible, so we don't have to add any checks or anything. And let's define pi is the partial score of the ith problem. Okay, now let me scroll up. Then you define your set int score for this problem, and this is nothing but see, if you think about it, set is also an overkill. You could have just iterated over all the scores for this problem and then be done with it. But why not? Let's just create the set. It doesn't matter. So now you have something like solved count is equal to, you could either solve 0 problem or you could solve all the problems. Solved count plus plus, and you do score for this problem dot insert solved count into partial score of this problem. So you have your both the sets. So you will remember that you had this set now score, and you have this set, and you have to merge and then create a new set. So let's do the merging. You define something like set int nxt score. That's how we usually do the merging and then replacing of the dp values. And then you do something like for integer now in score for this problem, and then you iterate over all the integer in the other part, which is this one, unique scores, all the older one. For integer unique, for integer old in unique scores, and then you have to just add the sum for both of them. So you do next score dot insert now plus old. Okay, so far so good. Then you have to, what does the problem asks you to do? Let's check. So it says that you have to print yes if it is possible to obtain an arbitrary total score between 0 and 100n. So you have to check if it is possible to achieve all these scores. And how can that be? The at the end Actually, now that you have created this next score, you have to swap it out with the older ones so that this next score becomes the unique scores, right? Because you are now trying to append a new element. So at the end, you return whether unique scores dot size is equal to, what do you want, 100 into n, right? Yes, so you want 100 into n. If this is true, you return true or false. I do it as bool. Actually, let me reduce the font size, and if it is too small, do let me know in the comment section so that from the next video onwards, I will try to increase the font size. Okay, now let's write the main function. So just some fancy tricks for not getting time limit exceeded error. And then you have to take the input for multiple test cases. So you do integer t, cin t, you do while t minus minus, and you have to just read the array in input. So integer n, cin n, vector in a of n, for integer i0, I less than n, I plus plus, cin ai. Okay, and then you do if solve of a. If the answer is yes, you print cout yes. Actually, you should use /n instead of endl, else you print cout no. And okay, looks good so far. Then let me copy the test case. I honestly have no idea whether this will even pass the samples. Idea looked correct though, but let's see. So I do g++ a.cpp. Okay, I need to go inside the temp folder, g++ a.cpp. Then /out in. Okay, it is printing no for all of them. So what is wrong with our approach? How come it is printing no? How can that be? Does this have an array of length? Okay, so the smallest is, so it should be yes, no, yes, no, yes. Okay. So let's take this input only because this seems easier to debug. I will take this. Okay. And here it says it is actually possible for every integer k, it is possible to achieve a total square of exactly k, because there are 100. Okay, this actually makes sense. So now we are debugging. Okay, let me do the debugging in a separate page. So we are debugging. So the test case is 220. So of course you can, this has the partial score of 1 and this has a partial score of 100 by 20 is what? 5. Okay, so with 1 comma 5, you know that if you solve 0 subtask of this, then you end up with 1, and now you can create everything from 0 to 100. Okay, but you wanted to create everything from 0 to 100 into 2, right? So 0 to 200. So this should also be possible, because since you can create everything from 0 to 100, and from here you can also create, you would need to create, let's see if our idea actually works or not. So for the first problem, what are the number of unique scores that are between 0 to 100, right? And for the second problem, what is the number of unique scores? So the number of unique scores will be simply, what did we put in our array? Let's check. We put solved count into pi. Okay, so that's fine. This means, so solved count, so there are 20 subtasks and pi is 5. So it could either be 5, and then it could be 0 into 5, or it could be 1 into 5, 2 into 5, 3 into 5, 4 into 5, 5 into 5, up till 20 into 5. So let's see if merging these two sets actually produce all the 200 entries that we wanted, or is our merging strategy actually incorrect and we have been following the wrong direction. So which is the case? I don't know. Let's check. So this is 0, this is 5, 10, 15, 20, 25, and so on. Now, if you want to create, like, let's say 100 plus, so if you want to create, like, let's say 123, would you be able to do this? Yes, because I think here you can anyway get the complete score of 100, and here you would be able to create anything that is missing, right? So it could be 23 score over here because the partial score is 1. In fact, pi is equal to 1 might be a very special case. Maybe the trick is to deal with pi is equal to 1. Maybe the answer is actually yes, if pi is actually equal to 1 for any of these, otherwise it might not be possible. But that's just a hunch. But okay, let's see why our algorithm did not work. So it should have worked, I think, because we are trying to sum up. So we'll, for each value x, we would have been doing x plus something from the right hand side, and something from the right hand side. So right hand side can definitely produce 100, right? That we know. And left hand side can produce this. So when 100 will be merged with all of these, it should have, yeah, it should have definitely resulted in, yeah, it should have worked. I think 0 till 100. And when you merge 100, it should have produced like 100 to 200. And when you merge with 0, it should have produced 0 to 100, which is the entire set. I don't know why it didn't work. Probably some bug in our code. Let's check. Okay. So score for this problem is this, and old is in unique score. Swap next score and unique score. Hmm. Too complicated, man. 100 into n. Actually, I would be very curious if that is what's happening. So how many integers are there between 0 to 100 n? So there are actually b minus a plus 1 entries, right? So it should have been something like this: 100 into n plus 1. The set size will be 1 extra, right? Is this correct? I think they should be. Yes, we got it. Now let's try the entire test. So yes, no, yes, no, yes, yes, no, yes, no, yes. Okay, we pray to God and we submit. I go to the submit section. No, I can submit from here. Hmm. Let's hope this works. In the meanwhile, let's also. Oh, nice. It actually worked. That's very interesting. I mean, I would say that maybe my solution is an overkill, like using the DP like approach and then transferring all these and then merging them. But I've seen this problem a lot of times, and I hope my solution does not get TLE because of unnecessarily using sets and all. But I think set will still be required. I think set is actually helpful over here. So yeah, I think let's have a closure on this. Let's move on to the next problem. We spent way too much time on the first problem. Definitely not good, but I will still see my standings where I'm actually uh, standing right now. What's my rank? 7,000. Hmm. Not good, but also not bad. Second problem is a tree one. Let's get ready for some trees. Huh. Okay. At least the problem statement is simple. So again, we'll follow the same strategy. How much time do we have left? We have 1 hour left. 1 hour 37 minutes. Hmm. Okay. If you are lucky, we will be able to solve A as well as B. That's a good thing. Let's check. First of all, let me yeah, let me extract just these info into the current page. And the way I deal with these kind of problems is I don't actually read samples at first. I read the problem statement. I believe whatever my interpretation is, and then I go in blind, try to okay, some announcements, ignore. So yeah, I was telling that I go in blind and I try to see whether my logic actually works on these samples, and I am actually not influenced by these samples. But anyway, enough of that rant. Uh, so let's see. You are given an array A consisting of n integers. Okay. You need to perform exactly m operations. So one thing you notice, like these kind of problems, I also told in my earlier videos that these are getting increasingly more popular in competitive programming, where you need to do some operations in a certain order. So you need to perform exactly m operation. Okay, we'll remember this. M is what? Less than 10 to the power 5. Okay. Each operation consists of two steps. Specifically, in the ith operation, you are given an integer xi, and you will, what will you do? First, let's select a center index u. Okay. Actually, let me move this over here so that we can do some whiteboarding as well. So you first select a center element. This is node u, and a non-negative length y such that the interval u minus y to u plus y lies entirely within 1 to n. What is it even trying to say? First select a center index u, okay, and then a non-negative length y such that this interval u minus y to u plus y. Okay, so if you have select a node index, no, not really a node index. I think they are just talking about a center index, and so this interval. So if you draw 1 to n on the number line, So they are just asking you to select u minus y to u plus y. So this is u minus y and this is u plus y. This should entirely lie between 1 to n, which is, I guess, fine. U minus y, u plus y. What is the interpretation of, like, what does this interval actually look like? What will be the size of this interval? That will be u plus y minus u plus y plus 1, b minus a plus 1. The same mistake that we made in the first problem. U and u cancels out. So the size of this interval is 2y plus 1, regardless of which u you are selecting. So this means that you are just selecting a center index u. Okay, now I get it. So you are selecting a center index u and then you are moving y steps forward. Okay, now this is the correct interpretation, and then y steps backward. Okay, this actually puts things into a bit more perspective. Then they are saying swap the elements a of u minus I and u plus I. Now what does this mean? Okay, so now I think they are trying to reflect this as a mirror. So this is a mirror, and they are asking you to swap this element, which is u minus y, with this element u plus y, and this element gets swapped. So here they are saying that you walk as many steps forward, you walk this many steps here, the same number of steps over here, and you swap both of these elements. Okay, so we have a nice visual representation. That's good. And then what? Then mark the element at index xi. Okay, xi is given to you. If this element is already marked, nothing happens. Okay, note that the marks are on the elements, not the indices. That means if element is swapped with some other element by feature operations, the mark will stay on it. Okay, if this element is already marked, nothing happens. Okay, so after you do this swap, wait, uh, I thought this problem was about trees. Wait, what? I was going to draw notes and stuff and whatnot, but okay, this looks like just like normal operations on arrays. We should be able to solve it. So okay, so you are marking a particular index, not an index, but an element over here. You are, let's say, coloring it in green or something, and the mark will stay on it if it has already been marked, or otherwise you mark it. That's fine. After performing all the m operations, this means that a fixed index will get a mark. There is no strategy involved over here. Your task is to find the minimum possible sum of all elements that remain unmarked. Okay, actually there is a strategy involved because this center index u and this y, this is also not given to you. So you have to do these operations. Your task is to find the minimum possible sum of all elements that remain unmarked. So this means that you have to maximize the sum of marked element, because if you have n elements, see, minimizing minimizing actually, let me write it in a different slide. Minimizing sum of unmarked is equal to maximizing sum of marked. Why is this true? Because the marked plus unmarked elements form the set from 1 to n. So you can see that this equation will be true. Marked sum plus unmarked sum is equal to n into n plus 1 by 2, which is the sum of all the elements. So this is fixed. So what is the marked sum? This is nothing but fixed minus unmarked. So they are asking you to minimize the sum of all elements that remain unmarked. Minimizing this means maximizing the right hand side. So okay, now we can only focus on marking the elements in a strategy that maximizes our overall sum. And we know that how many elements are we going to mark? We could mark a lot of elements because in one round you could mark that same element again. But notice that the index in which you are doing the marking, that is already fixed. Okay, so this looks like an interesting problem. Let's explore. So you have this array, and in the ith round, suppose this is the index that you are marking. So remember, our goal is to maximize. In fact, let me write that down explicitly. Maximize sum of marked elements. This means, see, always start with a greedy idea in these kind of problems. It might turn out to be incorrect, but at least it will tell you why it is incorrect. So if you want to maximize sum of marked elements, you would not want to waste around. Why do I keep writing with this? Let me just type it out. Don't waste around. What do I mean by that? We'll have to see if this is actually, if this actually can be achieved, but ideally you would like to, so if this is the index xi, and let me just confirm that xi is the index. Yes, xi is the, mark the element at index xi. Where did it go? Okay. So if this is the element that you are marking, you would like this to be unmarked. Why? So that you, in each round, you mark at least one more element, right? But this might not always be possible, because what if you have to see, for doing that you might have to transfer a lot of elements from here to here, from here to here, and if you do these transfers, then in the future round, remember that you are only allowed to do this operation only once for each round, right? So in each round you first do this operation and then you do the marking. So if you, in this round, if you be greedy and if you mark the element at this index, then what would happen? You, like, if you forcefully mark this element, if this element is unmarked, then you are good. If this element is unmarked, question is, should you keep it, or like should you utilize this shuffling or the mirroring to get some other element over here? Like right now we are talking about the case of unmarked. This element is unmarked. So if it is unmarked, it is not yet clear whether we should keep it, or, so right now it actually looks like that, okay, if it is unmarked, no need to do the operation, or do we have to do the operation? You have to, actually you have to do the operation exactly once, but can you you have to select a non-negative length. It means you can select y as 0. It means that you don't actually have to do the swap if you don't want to. So that's good. It means skipping that round and simply marking it. So at first glance, this might look obvious that if this element is unmarked, you don't do any swap at all and you mark this element because you are gaining some benefit. But it might not actually be correct, because suppose, see, all of this boils down to this fact, like if you had one round remaining, what would you have done? If you had only one round, then if the element at this position is 1, you would have forced it to become n, no matter what, because one round is your last chance to get your maximum sum marked. So if it's unmarked, it's not clear whether we should keep it or we should swap it with some other element. And in fact, if it's unmarked, doesn't really mean that we should swap it greedily. I mean, we could. Mm, we'll have to see. We will have to see whether this idea is correct or not. So, okay, what are the other possible things that we could explore? Maybe start by looking at one round and then two round and then three round and so on. So that might help us actually, I think. So if the total number of rounds is just one, so if this is round one, then if this is the index that you are dealing with, this is x1. And of course, this element right now is unmarked. So what would you do? You would find out where n is in this array. Suppose this is the n. This is the location of n on the left hand side, arbitrarily assuming. And then you have to do the swaps. So you will only mark, you have to just make sure that n reaches this node, and rest of the elements we don't care. So you could just create, see, previously we saw that you swap the boundary elements as well. This gets swapped with this gets swapped with this, because they said that I could be less than or equal to y. So this means if you can create a boundary, then we should be good, right? Like we could swap n with x1 and be done. How much time actually do we have left? Let's quickly check. 1 hour 20 minutes. Enough time to solve this problem, I would say. So, okay, if you swap this with x1, then this length of the interval, we saw that the length of the interval should be 2 into y plus 1. This length should be an odd number so that you can create this mirror. One thing has to be satisfied, like if n is present at this location, like see, if you have something like this, n a b and then this index x1, then the length is 1 2 3 4. So if n is even, you can see that you actually cannot do the swap because you have to select a center index and there is no center index. So this means that it's not possible to bring n over here. So is there a different strategy to bring n over here? Actually, this seems interesting because even for round one, even for just one single round, the answer is not obvious. In some of these problems, the answer is obvious for a single round, but n is round one itself is turning out to be interesting. So let's see what we can do about it. So one thing's for sure, like if you compute the distance between n and you compute, so you compute, like let's say index, you find out the index of n. This just means what is the index of n, And actually, will all the elements be unique? Consisting of n integers, you need to perform exactly m operations on A in order. Actually, elements can. What is this AI? Okay, so AIs are just the value. Okay. Oh, okay, okay. So my bad. So sure. N cannot be located over here. We were looking at it from the wrong angle. So elements can be anything, but they are saying that the all the elements start like so. So there are just these indexes only. So n will always be available over here, nowhere else. There is no duplicate copy, nothing. N will always be available over here. So index of n, this logic we actually don't have to check. So if n is available over here, then what is the distance of x1 from n? So you compute this, the size of this set x1 comma n. What is the size of this set? This is nothing but n minus x1 plus 1, b minus a plus 1, because both of them are inclusive. Then if this is odd, then you are good. Because you can actually bring n over here with just one swap. But if it is even, if it is even, actually I think we are going in the wrong direction, because yeah, actually all of this that I said, this is not correct, because I kind of misinterpreted the problem. So they are not asking you to color the indices themselves, they are asking you to color the elements, right? So the sum will actually not be n into n plus 1 by 2. So let me start from scratch for this problem. So you have something like max. No, you actually have an array to begin with. I think we got it all wrong. I mean, not we, just me. But this was the scenario. Like you had an array, and in one operation, like if you are only dealing with the round one case, then you could select one index, and you can create a partition, and like select a center index u, and then you can create a series of swaps. Like you have to place a mirror over here. You have to place a mirror, and then you have to swap these endpoints. Okay, these endpoints you have to swap. And again, but even though I was wrong about the problem interpretation, but you will see that the idea is kind of still correct, that minimizing minimizing the sum of marked elements. Let me again double check that that is what the problem asks you to compute. Copy it, paste it over here. So it says your task is to find the minimum possible sum of elements that remain unmarked. So minimizing the sum of unmarked elements. This is the original. And you can see that marked plus unmarked is equal to sum of array. So this reasoning still holds. This means that minimizing the sum of unmarked means maximizing the sum of marked. So now with that out of the picture, we know that maximize the sum of marked elements. Okay, how do we do this? So, okay, we were dealing with round one. Now for round one, again the logic is kind of sound that this time we have to suppose this is the element that we want to color. This is the index that we want to color, like the element at this index that we want to color. And if this element is not equal to the maximum element of the array, if it is equal to the maximum element of the array, we should not do the first operation because you are allowed to select y as 0. So you are good. But if it is not equal to max, then it means that you have to swap it with some element. So suppose max is located over here, and there can actually be multiple copies of maximas. This one, this one, this one, this one, this one, and so on. So if any of the copies of the maxima creates an interval of odd length interval. Why? Because we saw that the length of the interval was 2y plus 1 because every element is mirrored except the mirror itself, like the center of the mirror. So if the length of the interval is odd, we select that one to be the maxima. We select that interval and then we select the central element as the mirror and we swap this and this. So in that manner, this colored element will always be the max. So right now we are only solving for one round. We should have the correct strategy for a single round even before trying to solve it for multiple rounds. Consider this as an easy version of the problem. Okay, but what if all the intervals, all the places, all the occurrence of the maxima lie at even length interval? Then you are in trouble. You cannot achieve maxima. Then you repeat. You have to see if you can accommodate maxima. If you can, you should. Then you can see if you can accommodate the second maxima. If you can, you should. So for round one, the strategy is clear. You keep the unique you keep the unique elements sorted in decreasing order, like this is the maximum, let's say infinity, and this is like let's say minus infinity, and you check all the indices for this element and check whether the distance from all of these indices is uh, even or odd. So in fact, how do you actually check all of them? So you will, even though we don't have to implement it right now, but you will realize that x minus y, what you are interested about is whether they are even or odd, right? Even or odd. So sorry, you want to check this x minus y plus 1, like this difference plus 1. So this means that you want to compute this quantity x minus y plus 1 modulo 2, and this means that this is just nothing but x modulo 2 minus y modulo 2 plus 1 modulo 2 and the entire modulo. This means that for each maxima, you don't actually have to track all the occurrences. You only have to track the, is there a maxima in an odd place? Is there a maxima in the even place? That's all you need. And this way, you will be able to find the answer in O of n. Actually, for the round one version, it doesn't really matter whether you maintain this even and odd thing or not. Why does it not matter? Because of amortized time complexity. Like if you had this thing, then the total number of indices that you will traverse and then compute the answer for will be at most n. So even though you have n entries over here and worst case n entries over here, this is like the adjacency list. So in that manner, we would have solved only round one case, which is good. And that algorithm looks sound. There is no flaw with it. What about round two though? I think that is where things get a bit more complex, and we have 1 hour 8 minutes remaining. So for two rounds, let's see if any greedy strategy works. I mean, it's not a difficult problem since it's the second problem in a div 1 plus div 2 round. So for round two, see, in each round, you would of course want the maxima to, uh, yeah, in each round you want the maxima, the remaining uncolored maxima to be colored. But see, you could end up negatively affecting the other elements, right? But let's see, do we actually end up negatively affecting other elements? Like if this is u, and this is u minus y, and this is u plus y. So right now in round one, we saw that for round one, you don't actually have to track all the occurrences. You just have to track the even occurrences and the odd occurrences, right? So right now, when you do the swap, does it actually change the parity of the index? Because that is actually what matters, right? Whether you can center something around that element or not. Does it actually do that? Can we check that? So let's see. If you have this interval, like let's say the mirror is here. Mirror is this 2, 3, and 4. So this, so suppose maxima resides over here, and this and this are empty. But then after you do the swap, you see that maxima resides over here. So the parity has not changed. Okay, so I think we are going in the correct direction. Maybe I am pretty sure that this problem deals with parity. How did we know that? From round one. So again, let's try some, like let's say interval starts at this 3, 4, 5, 6, and 7. So 3 will go to 7. So the parity actually has not changed. So this is very interesting. This means that in the first round, you can be greedy and you can bring the maxima over here. If the maxima, like you can decide based on the parity of the maxima, that's fine. And you can bring a maxima over here in the first round because that's the best you could do. And after doing the swaps, notice that the parity of none of the elements is changing. This is actually very interesting. I think we are on to something here. We are on to something here. So, and in round two also, if you are not disturbing any, if you are not disturbing any elements, then you are good. Like if you want to color an element over here, you find out where the next maxima resides. If it resides in an odd interval length, you bring it over here, right? And you will not touch the parity of other elements. Can we formalize this? Can we formalize this? So we'll do something like, you will have to maintain something like this. Like this is, how should we reword it? Like let's say, this is infinity and this is minus infinity. So for each unique element, you will have to maintain the count of, odd 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 indices, comma frequency. Why are we maintaining the frequency? Because every time you can consume one infinity and you can add it and you can color it. By infinity, I mean the maxima. And you can store the count of even indices with frequency. So right now what I'll do is actually, so first of all, each time you want to do an operation, like suppose this is the operation that you want to do, then for each xi, I will locate all the maximas in order, okay, in descending order, and if any of them has frequency not equal to 0, like if frequency is still remaining, I'll see if it is possible to swap. So when is it actually feasible to swap? Let's see. So if the element, if you want it at index 5, right, can we formalize whether the maxima should be, so this itself is odd, right? So can we formalize whether parity equal leads to a swap or parity unequal leads to a swap, right? Can we formalize? So let's say if you have this 5, then this is index 4 and this is index 3, you can select this is a mirror and you can do a swap. So this means that swaps can only be done by the same parity. So let's write it down so that we don't forget. So one crucial observation is that you can swap any two elements of the same parity. So if you can only swap two elements of the same parity, then uh, in round I, you can take a greedy. And why will greedy be correct? Greedy can only be incorrect. Previously, I talked about my doubts about whether greedy will be correct or not, because it might end up affecting other elements and they might not be able to swap. But notice that since you are not changing the parity of the indices, other elements are literally not being touched. So why not take the best that you can at each round? So you can swap any two elements with the same parity. So in each round, you iterate this list from top to bottom and you check if any of these has parity equal to the parity that we are dealing with, right? Which can only be 0 or 1, right? Depending upon whether the index is odd or even. And then if this doesn't have anything, you go down the list. If this also doesn't have the same parity, you go down the list. So you will see that this algorithm is O of n square, because in the worst case, everything has an odd parity and the last element has an even parity. So we can do this optimization later, but let us first confirm that this idea is correct. So let's first implement a naive brute force kind of thing. Not really a brute force, I mean the optimal solution, but bit not good time complexity. So okay, let's do that. Let me open b.cpp, copy this template from here, remove all of this. This is solved, and the input would be n array, the number of operations in x size. Okay, that's fine. So let me see, you have vector of int a, and then you have vector of int in x. X represents the indices that you select in each round, and you don't actually have to propagate the size of this vector or this vector. You can just infer. How much time do we have left? 1 hour. We should be able to solve. So n is equal to a dot size. Okay, and now we want to maintain this vertical list, this one. So you do something like you want to maintain something like, for each element, how many for each maxima, how many copies are there for the odd frequency and how many copies for even frequency, right? So you could do something like map of int. So the integer will represents the maxima or the minima that we are dealing with, and the value would be what? That will be, let's say, pair int, and we'll have a convention you store should we store even frequency first? Let's say, yeah, this will have even frequency and odd frequency. Okay. And okay, that's fine. This is the frequency array. And why are we doing this? So yeah, so that pair dot first, you could also do that, but I think you would be better off if you just stored a DP array, sorry, a 2D array of length 2. Would that be better? So that we could easily do something like frequency of element of 0. Can we do something like this? Yes, I think it's actually better or easier to store it like so. Vector of int 2 comma 0, right? Okay, okay. I see we are not allowed to define a size over here. That's fine. Yeah, now we don't even have to have the convention. The 0th element represents, of course, even frequency. First element represents the odd frequency. So we just iterate the array for int I0 I less than n, I plus plus. Now the element that you are dealing with is AI. So you check not if map dot count AI. So if it already exists, if frequency, if this already exists, then it means the vector for this has been created. So you just get the vector and you update frequency of AI, and this is just I modulo 2. So if this is an even index, you will update the 0th frequency. If it is an odd index, you will update the odd frequency. And if this element does not exist, you create it. So you will do something like vector of int, vector int now 2 comma 0, and you do, okay, so here we have to do plus plus, right? And here we do now of I modulo 2 plus plus, and you insert it frequency of A of I dot pushback no. So now the end with okay, not really pushback, you have to do is equal to this. Okay, so we have this vertical stack thing that we just discussed. Now just process in greedy manner. So how do you process it? So you do for int x in, you can do something like x queries, or like indices, you could say indices for integer x in indices. And here, like, I will remember to keep these indices in a 0 based format for so that it's easy for me for integer x in indices. And you have to just iterate this map in a sorted order, right? And how do you do that? You can do that via this rbegin construct. Okay, so you also maintain your colored count, integer colored count, sorry, you want to do long colored count is, sorry, colored sum, marked sum, basically you want to do marked sum is equal to 0, and you are iterating over all the indices, and you want to check from maxima to minima. And how do you iterate from maxima to minima in a map? You use the concept of rbegin. So you do auto itr is equal to frequency dot rbegin, frequency dot rn. This is the way to sorry, this would be ITR not equal to frequency dot Rn ITR plus plus, and then you have to check if the frequency, you have to check if, so the parity that we are looking for should be equal to the parity of X, right? So you check the, you check frequency of current max is nothing but frequency of current max is ITR second, and this will give you the vector, and you want to extract the value of that vector at position x modulo 2. So see, now it's becoming very helpful, right? Otherwise, if we would have selected pair intent, then I don't even know what to say. Okay, just adding a bracket around this for safety reasons. Sure. And then you check if frequency of current maxima is greater than 0. Then you accept this, like no need to go down any further, and you decrement it. So you do something like ITR of second of x modulo 2 minus minus, yeah, and you break out of this because you have found your answer. Otherwise, if you have not found your answer, go to the next maxima, and since you have found your answer, you will do something like marked sum plus equal to what is the current maxima that we are dealing with, that is nothing but ITR dot first. And if you don't find a valid match, doesn't really matter. Or does it matter? No. Yeah, if you're not able to find a valid match, like you are not able to swap any element that is not already colored, then well, you didn't really change anything. So the marked sum will not change. And you have to print what? For each test case, output the minimum possible sum of the unmarked elements. Okay. So you print something like long total is equal to accumulate a dot begin, a dot end, 0 LL. Don't forget this LL, by the way. Common beginner mistake. So you print total minus marked sum, and you do this. Let's see if this is actually correct. If this is correct, we'll submit it, we'll verify it, and then we'll do some optimization to do some fast lookup in this section. Now here you want to scan the array. Okay, what is the input format? Let's see. NM, AI, and XI. Okay. You have integer NM. You have vector int A of N, X of M. For integer I0, I less than N, I plus plus, C in AI. For integer I0, I less than N, I plus plus, C in XI. And then you should actually do xi minus minus, because if you remember, I am just blindly iterating over the indices. So I wanted to add a comment saying that this should be 0 based, not 1 based. So that's fine. And then you simply call solve a comma x. Is this actually correct? Now is the time to verify. Open this. You do g++ b dot cpp, and 6 minus 18 minus 309. Okay, not quite correct. Do we have a small sample? So it says on this is 4 rounds, 4 rounds, 5 rounds, 5 rounds, 3 rounds. So I think this sample can we investigate because there are only 3 rounds. Their answer is minus 25. And our answer is minus 22. How come? Oh, actually, should we consider the case where we are swapping an element with itself? I think that should also be fine. I don't see any issue with that. Okay, let us investigate the bug. How do we investigate? Do we want to debug or do we want to what do we do? Frequency of AI filter now. Okay, let's print something like this. You do cout round in this round, this element 1, and you print the value of that element that you want. The value would be what? ITR dot first. Okay, and you do an endl. So here we'll have to add 1 as the test case number. So in the first round, they are saying -1, 1, and then -2, and then -3. And okay, they have not described the last test case, so I guess we'll have to figure this out on our own. But okay, we'll see. So I copied this input from here. Create a new page for debugging. Okay, that's not going too well. Okay, so it says this. Let me copy this. Okay, I don't know why copy paste doesn't work, but it says -1, -2, and -3. So is it possible for these three elements to win? So in the first round, -1 is winning, then -2 is winning, -3 is winning. But what is the original array? Actually, I can just do this, and then copy this part, add to current page. Now, of course, -1, they are saying okay, so in each round, they are saying that they should be able to swap these elements, and that's why the maximized sum of the colored element would be -6. That's what they are claiming, and the total sum of the array is 7 into 7 plus 1 by 2, which is 7 into 8 by 2. 7 for 28. So 28 minus 6, that's what they are claiming, and they have printed. No, -28. Sum is -28. And yeah, so we have to print -28 plus 6, which is -22, which is what we are printing, right? And they are claiming that they can achieve -25. How can they claim, how can they achieve -25? If they are able to achieve -25, this means that they are coloring how many elements? -28 plus 25, which is -3. So their maximum sum is -3. So they are achieving a better sum than us. How come? So they're saying the first element in the first round you okay, so you have -1. So -1 has frequency 1, -2 has frequency. No, not really the frequency. I think we should look at the indices, right? How much time do we have left? 44 minutes. Hopefully, I will be able to fix my bug. What's going on over here? Okay. Let's first of all figure out what is the optimal strategy to achieve this -4, -5. -6 and -7. And in the first round you have to color this, second round color this, third round color this. So our strategy is coloring all of them and saying that the maximum sum that you can color is -6. But they are claiming that the maximum sum that they can color is -3, right? Oh, I see now. Actually, so they, okay, so actually something interesting. So if the maxima is negative, then why would we want to color the maxima, right? Because you want to maximize your sum. Why take a negative element at all, right? So you have sorted all the elements. So in the sorted order, the so you will have 5, you will have 3, you will have 2, and then you will have -1, and then you will have -5, and so on. So if you can take this, good. If you can take this, good. If you can take this, good. But should you actually take this? Should you actually take as negative maxima? Not really. That will actually decrease your sum. But what if you didn't have any option? You do have to color one element though, right? So definitely some corner case we are missing for the negative maxima. So if you do have to take a negative maxima, what would you like to take? The element which is the element that can decrease your sum by the smallest amount, right? Which is this -1. And so in first round you can use -1. In the second round you have to swap it with something, but that element have to be at the same parity. So at this index you would prefer to not actually color anything because all the elements are negative. In fact, like if there is at least one positive element, can we always bring that element to this position that we don't want to color? That might actually not be possible. So you need to know if there is at least one positive element that is on the same parity, right? If there is, then you are good. Like you don't have to you don't have to do anything in that round. Otherwise, you have to take one negative element, that is for sure. But what I'm wondering is like how are they achieving this answer of -25? Maybe I'm missing something. So again, 7 into 8 by 2, 28, and they are claiming that the minimum sum of unmarked element is how much? -25. This means the maximum sum of marked element they are claiming is -28 plus 5, which is -3. So how can you create -3? -3? Oh, I see the strategy now. I see the strategy. So what they have done, I think, is here in round 1. Yeah, so in round 1 you color -1. In round 2 you color -2, and in round 3 you color this -1 again. You bring it over here because you are allowed to swap two elements of the same parity without affecting any other elements at all, because only their parity matters. So that's why in round 1 you are forced to take an element. So you took the smallest element available. In round 2, you are forced to again take an element, but you can only take the smallest negative element on the same parity, right? Because if there is at least one positive elements on that same parity, then you can take that positive element and your algorithm will actually work right out of the box. Otherwise, if you are encountering a negative element, then you have to think about that differently. So maybe the correct algorithm, no, not really maybe, I think it's pretty clear what's happening over here. So we have to check whether this element that we are dealing with. Now you also have to maintain for all parity. Is there a, for all parity you have to maintain what is the maximum element. So you have to maintain, you maintain vector of vector int mx of 2 comma, yeah, of mx 2 comma 0 for all element. What is, what, for any parity, what is the maximum element that is available over here, and you initialize it with actually minus infinity, and you define minus infinity as const int infinity is equal to 1 in 9 plus 1, 1 in 9 plus 1, yeah, minus of this. How much time do we have left? 36 minutes. Okay, we have to do it fast because we also want to do the optimization. Oh, so you initialize it with, okay, my bad, I just want to keep infinity like so and then use minus infinity. And here you just encountered an element at parity I modulo 2. So you do something like mx at I modulo 2 is equal to max of mx at I modulo 2 comma a of I. So this way mx of 0 means the maximum element at an odd parity, and mx of 1 means the maximum element at an even parity. Sorry, mixed these up. I mean, you didn't really need a vector, but anyway, means the maximum element at any odd parity. Why is it not allowing me to do max? What? Mx of I modulo 2. Okay, why am I maintaining a vector? It should just be this vector of int. Okay, now it's correct. Now, so if you reach a negative element, you simply don't want to take it, right? But you might be forced to take it, correct? Otherwise, color an element that is already colored. So you might want to add an early break over here, something like if frequency, if actually you defined current max is nothing but itr dot first, and let me use that variable over here. And if this current max is less than 0, you break, and then you remember how did you break this loop. Bool abrupt break is equal to false, and here you set this abrupt break, because if you do an abrupt break, you still have to swap it out with at least one element, right? So you have to swap it with the maximum element on that, be it a negative element, right? It could be a negative element, that's fine, but you do have to swap it. So here you do if abrupt break, then you do mark sum plus equals to current max, sorry, mark sum plus equals to mx of x modulo 2. But you have to use this, but again, like, it's complicated actually, because the element that you have just colored it with, was it already marked or is it being marked for the first round, right? You have to remember that. How do you do that? Hmm. Only 30 minutes remaining. How to solve this problem of not taking the negative element? How do we solve this? How do we solve this? Maybe let's go back to the drawing board, see if we can find anything. I mean, it's clear what we want, we are just not able to implement it, so that's just lack of practice, I guess. But I think the idea, we are very close to solving the original problem. Mm, how do we avoid taking the negative elements? So all of these elements we want to consider as these candidates, but these negative elements, they aren't really considered as candidates, because we want to maximize the sum. And if we are forced to, then we would rather take an element that is already colored, or take the lowest uncolored element. Yeah, so in that case, you just have to remember, is an element at that parity already colored? If it is already colored, you take that element, right? And then you will not change the sum at all. Otherwise, you will have to take the smallest negative element at that index parity, right? So yes, so this will still be helpful. Now okay, so we'll actually remove this abrupt. Yeah, so if this current max is 0, so now this time you maintain, you do something like mark count. So you count how many elements at odd parity are marked and how many elements at even parity are marked. And every time you encounter this, at the end, you do something like mark count of x modulo 2 plus plus. Okay. And if a situation arises, why the hell is it complaining? So marked count of 2, marked count is undefined. Okay, I have selected it like so. And every time you encounter a situation where you are trying to locate the maximum but you hit a negative element, then you check. You have to end your journey right here, because no point in considering the negative elements of the candidate. So you check uh, if marked count of x modulo 2 is greater than 0, if at least one element has been marked, be it positive, be it negative, you can simply skip this round, right? So if mark count of this is 0, you simply break. Else you do, I mean, you will break in either case, that's fine. Yeah, I think you have to do this. If mark count of x modulo 2 is equal to 0, then you increment your answer by mark sum plus equals to what is the max at this frequency, which will of course be an odd number. Why cannot it be an even number? Sorry, which will of course be a negative number. Why not positive? Because if it was positive, then we would have used that element, and if you have used it in the past already, then this wouldn't have been 0. So you do mark sum plus equal to this, and then you break, and this abrupt break is not needed anymore. And a marked count of x modulo 2 plus plus, that is also fine. Yeah, I think okay, let's check this. Minus 28. Still incorrect. Why is it still incorrect? Okay, I think yeah, so here you actually have to current max is less than 0. Let's do something like this. Payout and then so it, yeah, so it is reaching there correctly, but then what are we doing? Are we not increasing the marked sum accordingly? So yeah, we are increasing the marked sum by, okay, mx is equal to, okay, we had to initialize mx with minus infinity. Our bad. Okay, that makes sense. Okay, now it's minus 3. Okay, that is good. Let's quickly check the samples once again. 6 minus 20 minus 362. Yes, minus 637 to minus 25. Okay, how much time remaining? 25 minutes. So we'll quickly submit it. I know that it will TLE, but we'll gain some confidence. Let me quickly submit it. And in the meantime, now let's worry about how to avoid doing this iteration, right? How to quickly find out the elements that are still remaining, right? And how can we do this? So notice that in each round you are deleting one element, right? So if the frequency becomes 0 and you actually remove that element from the map, then you won't be iterating that element anymore, right? So can we do something like maybe just delete that element from the map if the frequency is 0, so that that max is not even considered as a candidate in the future? Can we do that? I think that should help, because anyway we are breaking at the first one, right? And whenever we break, we increase the, see, whenever we break, we decrease the frequency by 1. So this means that we can only break as many times as there are elements in the array, right? How do we deal with this case? Like how do we deal with the case where all the elements are of odd and this smallest element which is greater than 0, but this is at even frequency, and all the queries are something like 2 2 2 2 2 etc. So each time there will be no deletion, but you will still have to traverse this entire list. So this means that you will have to maintain the odd frequency and the even frequency in a different map. 23 minutes left. So okay, time is ticking. So if you maintain them in a different map, then I think it's very easy. So then you just have to iterate the elements of this map, and every time you iterate one element, you like remove the frequency by 1. Every time you iterate the other element, you remove the frequency by 1, and so on. So this means that every time one deletion will happen, so the amortized time complexity will be O of n log n only. Why? If you actually delete this element from the map once all the copies are exhausted. So let's try out that idea. Why not? So instead of now maintaining a frequency array, you will have to do something like uh, even parity frequency. Or now I think we can do something like map of, this time map will be at a vector int. Okay, is it actually allowed to hash vectors? Is it allowed? I don't know. Or we can do something like this, vector of map of int. Okay, and we'll just maintain as frequency p, means frequency p, frequency with p means frequency with parity, and we could do something like this. Instead of doing frequency of a of I is equal to now, we do something like frequency with p, which map to select, I modulo 2, and then in this map, which element to select, a of I, and increment its frequency by 1. So it's simple. You select the first or the second map, and then increment this frequency by 1, and this time let's initialize it with an empty map, and yeah, let's initialize both the array, and then all the if and the else condition will also vanish. Just simple this frequency with p. And actually, do we want to maintain this? Okay, I mean, we have already computed this mx, right? Let's just maintain it. That's fine. And what we'll do this time is 20 minutes remaining. You got to do it fast. So you have updated the correct map with the frequency, and this time we follow the same algorithm, but this time instead of iterating this, we decide which map to iterate, right? So we do auto, you do auto and frequency is equal to, which map do you want to iterate? You want to iterate the map frequency with p x modulo 2. You get the reference, and then you still do your same analysis, and then this time what is the frequency? Frequency is nothing but frequency of the current maxima, that is nothing but itr dot second. Current maxima is nothing but itr dot first. That's fine. If current maxima is less than 0, marked count we need, this is fine as well. Frequency of current maxima is greater than 0, then we do this decrement. Yeah, so this decrement, now this is the interesting part. So you have to do itr dot second, okay, minus minus, because itr dot second is just the frequency. And but now here is the tricky part. This condition that I'm just going to add, this is what will make it the amortized of n log n complexity. So we'll check if itr dot second, actually let's not are we allowed to delete elements while iterating a map? Let's see. Bool, we can just, I'm just making a bit more complex, but at least it's verbose, but it might work. So we'll say that bool should delete element is equal to false, and integer element to delete is equal to, I don't really initialize it, and then we do itr dot, we do, if this is the last copy, if itr dot second equals to 1. Oh, actually, we do have to decrement, right? So that line has to exist. I hope this does the decrements in place. I would be surprised if it doesn't. But okay, so if this has now become 0, I don't want to risk uh, iterating the map. Or can we actually do the deletion? Is there any harm with it? First, let me check with just doing the deletion. I think it works. So we can just do frequency dot erase frequency dot atr, but actually this will alter this, but I think that's fine, because anyway we were planning to break the loop, so that should be fine. I will just delete this copy. Frequency dot erase. Wait, what? 16 minutes. Frequency dot. What is the method to erase? This is the method. ITR, or is it star ITR? Okay, so the map is on what? Int. Let me just delete by the first element. That should be okay. So I have deleted that entry from the map, and then that code is same as before. But now it's possible that the entire map is empty. But if the entire map is empty, you still have to color it, right? And you still have to color it. It means all the elements have already been colored, so your sum will not change, right? Your sum will not change, and negative case, will it be handled? Yeah, I mean, negative elements are never really deleted from the map, or are they deleted? Yes, they are deleted, but if all the elements are already colored and you don't want to look into the negative element, frequency of current, I think this should be fine. Let's check. So 6 minus 2, 360. 6 minus 20 is 362, minus 637, 2 minus 25. So yeah, so this should have the amortized time complexity of n log n. Let's check. I hope this works because we don't have enough time to fix it further. I think this shouldn't require fixing as such due to these early breaks, and amortized time complexity should still be of n log n only. I am sure of that. Yes, we solved it. So now I don't want to look at other problems. What is my rank? 5800. Okay, not bad. 5800. Okay. So yeah, that was it for the first version of this window. I am too tired to attempt all the other remaining problems. but I hope you got something to learn from the first two problems. Although I wouldn't say to approach it like the way that I did, but I just wanted to put it out there like how I would have approached it. And as you can see, I ended up taking the entire 2 hours just to solve two problems, which is not good, but at least hey, it's better than nothing, right? And by the way, this idea that I just showed you of amortized time complexity, hmm, it's very interesting that just the other day, like if you check the last video on my channel, that's exactly on this idea, what amortized time complexity means. And I actually discussed this idea in detail over there and how you can apply it to problems. And I find it very surprising and a bit of a coincidence that after uploading this video, I was able to apply this thing, the concept of amortized time complexity to this problem. Maybe it is an overkill, I don't know, but yeah, good to see. And I think I already walked through the thought process of this, and a lot of people might get confused how parity comes into picture all of a sudden. And right now you saw me like you saw me how I started with round one, and then how I concluded that parity comes into the picture. But yeah, I have solved these two problems, but I am not going into the editorial for these two problems. Like, I'm not discussing the details of the solution. I hope you were able to follow along. But if not, and if you need a video editorial where I don't give you my thought process but just give you the solution, do let me know in the comment section. We can think about bringing that kind of content. And yes, if you like this series, like this Thinking Out Loud series, if you want to see me struggling on Codeforces problem, do let me know in the comment section. I will try to do the same exercise for future Codeforces contests as well. Thank you.